Deep, deep beneath our feet, there is an engine. It's this colossal, slow-motion engine made of solid rock that flows like thick honey, but over millions and millions of years. This engine, the Earth's mantle, is what drives pretty much everything: volcanoes, mountains, even shoving entire continents around the globe. It's the hidden power source of our living planet. But that right there presents a huge problem, right? How in the world do you study something you can never ever see or touch or measure directly? Well, the answer is you have to build a virtual Earth. You have to create a simulation inside a supercomputer to try and model these unseen forces. And let me tell you, that is a task that is way more difficult than you might think. So in this explainer, that's what we're going to do. We're going to build one of these models ourselves, step by step. We'll start with the grand challenge of it all, then create a super simple base model. From there, we'll start making it more realistic by adding in real-world physics and, of course, the continents to see what kind of turbulent picture of our planet actually emerges. You see, the ultimate goal for geophysicists is to create what they call a general circulation model for the mantle. Think of it like the incredibly complex models we use to forecast the weather. But modeling the Earth's deep interior, well, that presents some unique and absolutely massive hurdles. And when I say hurdles, I mean it. For starters, we don't fully understand the fundamental physics, the rheology, of how rock actually bends and flows under such insane conditions. And our computers, as powerful as they are, just can't resolve every tiny crucial detail. Plus, the whole system is deeply chaotic. We're talking the butterfly effect, where the tiniest error at the start can lead to a totally different planet millions of years later. And the real kicker? We have very little direct data from the deep Earth to even know if our models are on the right track. So with all those challenges, where do you even begin? Well, you do what scientists always do. You start simple. You build the most basic, stripped-down version of the system you can possibly imagine. We're basically going to start by building a digital lava lamp and see what it can teach us. Now, to measure what's happening in our model, we need one key number, the Rayleigh number. The easiest way to think of it is as a chaos score. A really low number means you've got a calm, predictable flow, kind of like water gently simmering in a pot. A high number, well, that means you're dealing with a wild, turbulent, and totally chaotic system. So, what's the Rayleigh number for Earth's mantle? Get this, it's estimated to be around 10 million. That number tells you everything. We are not dealing with a gentle simmer. We are dealing with an incredibly energetic, complex, and chaotic system. So, our very first model is just a simple box of uniform fluid that's heated from the bottom. And what does it do? It produces these beautiful, orderly convection cells. You know, hot stuff rises, cools at the top, and sinks back down in this perfect, predictable loop. It's a fantastic start, but let's be honest, it's way too simple to be the real Earth. Okay, so our symbol box gives us these neat, predictable loops. But the real Earth is anything but orderly. It's messy. So now let's start adding some of that real-world messiness into our model, layer by layer, and see what happens. Our first big complication: the Earth isn't just being heated from the core below. Nope. Most of its heat is actually generated from within, thanks to the radioactive decay of elements that are mixed all throughout the mantle. And this completely changes the game. Instead of those stable cells, you get a much more chaotic system, where the interior is active and it's constantly forming these temporary, shifting plumes. This is our first real step towards what scientists call soft turbulence. Okay, next up, viscosity. The rock in the mantle isn't all the same consistency. As it gets closer to the surface, it cools down and becomes thousands of times thicker, more sluggish, more viscous. What this does is create a kind of semi-rigid lid on top of the churning fluid, and that is a crucial step if we want to understand how tectonic plates behave. Now let's go deeper. About 660 kilometers down, the pressure is so intense that it literally forces the atoms in the minerals to rearrange themselves into a whole new, denser structure. It's what's called an endothermic phase change, meaning it actually absorbs heat, and it acts like a major barrier to flow. So when cold, sinking slabs of rock hit this depth, they can just get stuck. And the consequences of this barrier are pretty dramatic. It can actually split the mantle into two separate, leaky layers of convection for a while. You get all this cold material piling up on top of the boundary until its own weight becomes too much to bear, and then suddenly it can all flush through in this catastrophic, avalanche down into the lower mantle. This makes the whole system way more episodic and unpredictable. But here's something really counterintuitive that the researchers discovered. As they added these complexities one by one, the models sometimes got less accurate, not more. It just goes to show you that the Earth's mantle is this incredibly balanced system where all these different complex forces are often working to cancel each other out. Making a model more complicated doesn't always make it better, at least not right away. But, we've left out the biggest piece of the puzzle so far, the one thing that truly reshapes the entire system, the continents. They are not just passive rafts floating on top, they are active players that fundamentally change the rules of the game. It's all part of this incredible feedback loop called the Wilson cycle. Just imagine it. All the continents are drifting across the globe, and they get pulled toward areas where the mantle is sinking down. Eventually, they all crash together, forming a massive supercontinent. But this new landmass, it acts like a giant blanket, trapping the planet's heat. That heat just builds and builds until a powerful plume of hot rock rips the supercontinent apart, sending all the pieces scattering once more. So you see, the continents shape the mantle's flow, and the mantle, in turn, decides the fate of the continents. So after we've added all these layers of complexity, internal heating, that weird viscosity, the phase boundaries, and now the continents, what kind of picture of our planet actually starts to emerge from these models? Well, the final picture isn't a simple simmering pot at all. It's a deeply turbulent engine. It's a world that's driven by these cold, sinking slabs and hot, rising plumes, with these strange internal boundaries that create stop-and-go avalanches deep inside the planet. And most importantly, we see that the continents aren't just passive passengers along for the ride. They are fundamental architects, actively shaping the very forces that tear them apart and bring them back together again. And here's the really mind-bending part. All of this understanding, this entire complex picture we've built, it comes from two-dimensional models, which are still a huge simplification. It leaves us with this tantalizing question. If these flat models can reveal such a complex and dynamic world, what incredible new secrets about our planet's history and its ultimate fate are we going to unlock when we can finally model Earth's hidden engine in all of its three-dimensional glory?